Welcome back to Hypothesis Testing Done Right, Part 2 of 14. In Part 1, we wrote the two hypotheses. The skeptics know that Sam's true edge mu is 0 versus the alternative that mu is positive. Now we turn the messy data into a single number we can judge. The test statistic, by rescaling Sam's estimate into units of its own noise. Here is the reasoning. Sam's 8 basis points look small or large only relative to how much the sample mean wobbles from sample to sample. If daily returns barely vary, then 8 basis points averaged over 252 days is a mountain. If they swing wildly, it is a pebble. So a raw distance from the null, here, x bar minus 0, 8 basis points, is uninterpretable on its own. We must divide it by a measure of its own variability. Recall the central result from chapter 1.4. For independent draws with mean mu and finite variance, the central limit theorem says, the standardized sample mean converges in distribution to a standard normal. The denominator there, sigma over the square root of n, is the standard error of the mean, the standard deviation of x bar across hypothetical repeated samples. Note the square root of n, collect 4 times as much data, and the wobble halves. This is why sample size will matter so much. Now do the one move that defines a test. Assume the null is true and substitute mu equals 0 into the central limit theorem expression. Under the null, x bar minus 0 all over sigma divided by root n converges to the standard normal. This is the test statistic in its idealized form. Take your estimate, subtract the null value, divide by the standard error. The result is a pure number. Sam's 8 basis points expressed in standard errors above 0. A test statistic of 0.3 means the data sit less than a third of a standard error from the null, utterly unremarkable. A test statistic of 4 means 4 standard errors out, a place the null almost never visits. That single number is now something we can look up in a known distribution, which is the whole point. We have turned how far is the data from the null into a quantity we can compute a probability for. There is one honest problem left, and fixing it gives us the t. To summarize Part 2, a test statistic rescales your estimate into units of its own noise. It is the estimate minus the null value, divided by the standard error. The standard error, sigma over root n, comes straight from the central limit theorem, and that square root of n means more data buys a tighter, more convincing result. Assume the null is true and the statistic becomes a pure number. How many standard errors? Sam's average sits above 0, something we can look up in a known distribution. In Part 3, we confront the one honest problem with this idealized statistic. We do not actually know the true standard deviation, sigma, and fixing it gives us the t statistic you will compute every day.